Okay, so good morning again. And today there we have visitors from Los Alamos National Laboratory. They will visit your class at 9:45. And after that, you will have no lecture, so you can treat it as a break. Okay. So, but they will eat up rest of your lecture. But I will not be. I will not be teaching. Okay. So I think they are like here for recruiting, and you are like final year students, so maybe you can connect with them and ask questions if you are interested. Okay, so any questions from the previous lecture? It is scary because either it's mean that I'm teaching very well, everything is like you you understand everything, otherwise it means you don't understand anything and you're scared of. Okay, go ahead.
Can we just spend like 3 minutes going over soft affinity and hard affinity? Just
3 minutes going over what?
soft and hard affinity.
Soft and hard affinity. Okay. So remember the question is regarding the previous set of slides, which was about CPU scheduling, right? And the issue was like, yes, our scheduler, when we are scheduling multiple processes on multiple cores. So remember, so let's say you have only two cores, core A, core B. Each one of them have their local L1 cache, and they share the L2 cache, right? And we have four processes, process 0 to process 3, and we want to run them from core A and B. So now let's say our scheduler first selects, I'm not going into detail of scheduling algorithm. Let's say we are in a situation where P0 is running here, P1 is running here, right? And then let's say that P1 is accessing some data, it is doing some computation. Again, sum is equal to A plus B. And here you have memory. So all these are memory locations, right? So you have at some address which is named as in the memory, which is named as sum, another address which is named as B, A, and B, right? So let's say this is initially 0, this is 10, this is 15, right? Now let's say process P1 want to compute this one. So what it will do, it will first read A into its some register. Let's say register R1 is set equal to 10. But it needs to bring the data from all this hierarchy up to the register, right? Right? And then, so it leaves the copy of this data A all along the way. Like you have a copy of A here, you have a copy of A here, right? And then it brings the data B. So let's say register R2 is equal to 15, and it leaves the copies of, during the process, the copies are made at every level of hierarchy, right? So now let's say, now it has loaded the data into R1 and R2, but yet it has not calculated the sum. Because this is a high level language statement. When you break it into assembly language, there will be multiple instructions in order to achieve this computation. Now let's say that before it does the sum, so let's say the assembly is add R3, R1, R2. And before that, here were the instructions which were doing the loading of data. But before it executes this instruction, let's say it is kicked out. The process is kicked out, schedules another process, P3, right? On this core. So P1 is not running here anymore, P3 is running here. So P3 pollutes the data, right? Let's say even if it doesn't pollute the data, so P3 starts running here. And then when the P1 again gets the chance, So let's say by that time P0 is done and scheduler schedules the process P1 not on core B but on the core A. Now when it comes to the core A, so P1 is running here and it wants to do this execution, this addition, it cannot do this addition. Why? Because the registers of this core don't have this data because the register file is core specific. So you again first need to invalidate the cache locations in this L1, which were holding the value of A and B, and then bring the data again, at least from L2, if it is still available in the best case, still available in L2, right? So you are doing extra work. Why the source of the reason for this extra work is because previously you were running P1 on core B and now you are running at P1. So you need to again move the data into the L1. You need to make sure the data is here and then it is available in the registers. So which means that basically you need to first, and as a part of that, you also need to invalidate this data here. So you need to do invalidation, which is a very costly operation. And you also need to bring the data again, extra data movement, right? Extra data movement. So you are paying the extra cost. So what you do is that as one option to avoid this is that what you can do is you can say, okay, I don't want my process one when it runs for the second time to run on a different core. I want to run it on the same core. So second time I don't want it to run here. I want to still run on the P1 here or core B. Okay. So this is known as specifying the affinity. Soft affinity is the situation where kernel tries to achieve this, but doesn't guarantee you that it will always meet, it will always keep running the same process on the same core, right? But if possible, then it will try to do that. If not, it will like avoid it. It will not achieve that affinity. The hard affinity is where you specifically, explicitly, you require your kernel that no, whatever the matter is, I always want my process P1 to run on the same core B. Okay, and you can specify by using, for example, in the case of pthread, you can set the affinity by calling the API for a given process, and it is not necessary that you must specify only a single core. You can specify a single core for the P1, but you can also specify a set of cores. Let's say, for example, in my machine, I have, let's say, 20 cores. So I can say, okay, run process P1 at possibly at like P0, core 0, core 4, core 8, core 10. Okay. Maybe only core 10. Okay, so this is known as hard affinity, where it is guaranteed that your process will always run on the same core. Okay. Any other question? Hope I answered. Another question.
Does the scheduler itself have like hard affinity to make sure it doesn't keep track of where it's sending the messages?
Actually, if you don't specify explicitly, then the scheduler tries to balance the situation, because the issue with rescheduling is that, as I said, you on the one side you have to pay the cost of invalidation and extra DM. But if you always say that I want to run the same process on the same core, then maybe you are underutilizing your other cores. Okay, so depending upon the state of the system and the current performance parameter, kernel may try to achieve the optimum point, and maybe it involves scheduling the same process on a same core operator. So that's why it's like soft affinity, there is no guarantee. Okay. Any other thing?
So for multi-threaded environments, how should we handle like interrupt routines, interrupts that occur with them?
Can you elaborate your question a little bit more? What do you mean by handling the interrupts?
Handling interrupt, like what would happen if you have a thread, but that thread gets interrupted by another process?
By another process.
Yeah.
Okay. So it is interrupted by another process as a result of scheduling algorithm.
And like the result of like you have like a user level program that does like several threads, but there's an interrupt that occurs.
So now when you say the interrupt occurs, it can mean multiple things.
Yeah.
One, it can mean that there is a hardware interrupt. Second, there is a software interrupt, or the process or the thread you're talking about is interrupted in terms of its execution because of the scheduling algorithm. So it is kicked out. So still its execution is interrupted. The end result is same in all situations, that the execution of that thread is stopped at the point where it is, and then it will be resumed later in future, right? So these are like three different scenarios where you are saying that it is interrupted, but the mechanism of the interrupt itself can be different. In one, it is like originated by a hardware interrupt, in the other maybe by the scheduler, right? So, but in all the cases, as I said, what will happen that the execution of that thread, which is under discussion, that thread will be execution of it will be stopped, or it will be like, its state will be saved in memory. And once the source that is triggering the interrupt is handled, it can be another process, it can be a hardware interrupt. When once it is handled, then you will come back and resume from the same point. And for that, we already know how it's happened, that you store all the thread-related information in the memory, and once you resume, you restore that into the registers. Okay.
Wait, this is a very naive question, so I apologize in advance. But does this scheduler schedule itself to like copy the CPU every so often to make sure everything else is still following the trajectory, or where does the scheduler run?
Okay. Anyone want to answer this? So here is his question is this. The scheduler is an entity which is scheduling other processes, right? And then the question is how the scheduler fits in the whole picture. Is it also scheduled for its own execution? So anyone want to answer? Yeah, I also don't have 100% clear answer, but this is what my intelligent guess or my logical reasoning is. So your scheduler is definitely a piece of code. So it's need to run on as a process, most probably as a kernel level process. Not most probably, actually as a kernel level process. And then since it is responsible for scheduling other processes, so which means that we cannot kick it out. We cannot put it in the waiting state. So I would expect that it occupies a core in a like constant way, continuous way, without being interrupted. So what it is doing is that it keeps executing on a core or as a thread continuously on the hardware, and then its execution of the scheduler itself is not interrupted by the other processes, because it is not in the pool of those candidate ready processes. It is not a user level process, it is a kernel level process, and it is not competing with them. So this is like what I would expect. How exactly is done in, for example, Linux at the implementation level, I'm not sure. Recently, I submitted a paper like on the last Friday. So where I am basically also doing scheduling of multiple threads, kernel level threads. So the scheduler itself is implemented as a kernel level module. So that kernel level module, it keeps running all the time. That's why it is possible. It can schedule the other threads. Okay. But this is my implementation. How the actual Linux scheduler is implemented, I'm not clear on that. Okay. So I think let's go to the lecture. Otherwise, we already have visitors today. Okay, so last time in the lecture, we were talking about the Peterson's algorithm. We talked about the Peterson's algorithm, but we said that we cannot use it on the modern computer architectures. And the reason for that was that in the modern system, what we do is that the compilers, in order to get the performance improvement, what they do is, if possible, they reorder the instructions. And this reordering makes the Peterson algorithm fail. So how, so this was the Peterson algorithm. I'm not going over it again, but I am going to discuss the reason why it is not possible for Peterson algorithm to successfully achieve the mutual exclusion on the modern systems. So we are also actually, we discussed this problem, this example, if you remember, right? Do you want me to go through it again, or you are clear on that? Clear on that? Okay. So here the issue was that we expect the third one to print 100, but actually what it prints is it depends upon the reordering of the instructions by the compiler.
Or maybe I want to explain it again to clarify the context for myself and everyone else. So here you have thread 1, thread 2, and thread 1 has while flag. So if the flag is not true, then keep waiting, and if it is true, then print x. On the other hand, we have thread 2, which first set x equal to 100 and then set flag equal to true. So basically, if thread 1 is running here, what it will do, it will keep running in the loop, right? And then if the thread 2 executes this on a different code, and it sets x equal to 100 and it sets flag equal to true, then when it is running in the loop and it sees, oh, now the flag is true, so it can fall through the loop and it can print x, which is 100, right? But this is what we expect in a normal situation where compiler is not reordering the instructions. But if compiler reorders the instructions, so let's say that compiler thinks that if I execute this instruction first and this instruction later, then and as a whole, I can increase the performance. So what it can do is, what it does is that it sets okay, flag equal to true, and then it says x equal to 100, right? So now here, our thread 1 is, how to say, is in a loop. As soon as it sees like, okay, the flag is equal to true, so it falls through the loop. But also the other thing which we consider is that before our thread 2 is able to set x equal to 100, it is interrupted, maybe by another process or another thread. So then thread 1 not prints 100, it prints 0, which is not the expected result, right? Clear? So this, go ahead.
Was it the same optimization for
Yeah, we can definitely, we can do, but I mean, normally these optimizations are enabled, and when you disable these optimizations, then they are disabled for all the programs, not only for your particular thread. So maybe there are other programs which are not affected by reordering in terms of correctness, because here the correctness is affected. There are other programs which are not affected by reordering in terms of correctness, and they improve the performance. Then if you disable, then the performance is gone. Okay. So this same thing, the same thing means this reordering of instruction is the reason which makes Peterson's algorithm to fail on the modern systems. How? If you go here in this figure or in this slide, so here you have process 0. So what is process 0 doing here? Let me again write the process 0. So it is first, before entering the while loop, it is setting flag 0 equal to true and turn is equal to 1, right? Process 1, it is setting flag 1 is equal to true and turn is equal to I, right? Now, let's say that our compiler, what it does is that it reorders these instructions, these two instructions at the start of the body of the while loop, this while loop. Okay. So how? So for example, for process 0, what happens is that process 0, this instruction is first executed before the flag is equal to true, because the compiler thinks that if I execute this one before, or even actually the compiler cannot do reordering if your underlying hardware doesn't support reordering, okay, or out of order execution. So actually these are known as out of order processes. So if your architecture doesn't support out of order execution, your compiler cannot do the reordering. So we are assuming that underlying architecture supports it. So let's say the compiler decides to execute 10 is equal to 1 before this one. So now what is happening here, you have process 0 setting 10 equal to 1. And then what happens, let's say that also on the side of the process 1, this is executed out of order. So 10 is equal to 1 is first is 1, and then flag 1 is set equal to true, right? So, and in the meantime, this is the timeline. So what happens that process 0 executes, then let's say it is interrupted. It is kicked out from by the scheduler. Process 1 executes, so process 1 sees 10 is equal to 0, flag 1 is equal to true. So the while condition here, this condition becomes true for the process 1. Because what does this condition say? It says while flag I. So flag 0 and turn is equal to 0, right? So here, since this is so now this condition becomes true because turn is equal to 0. So this becomes true. This is true, and flag 1 is equal to, so here, this one. Because initially all the flag value is set equal to 0. So this is false, right? Since this is false, so it's mean your loop ends and you enter the critical section. Enter critical section. Let's say it is now in the critical section and then it is interrupted. And let's say the process 0 is executing. So process 0 after that, when it executes, it sees that flag 0, then it will set its flag 0 is equal to true. And the final value of turn was equal to 0, right? Because see, the turn is set equal to 0 by the process 1 after the process 0. So the final value is 0, right? So now what happens that the while statement for the process 0 also becomes true as a whole. The loop breaks and it also enters the critical section. So both are in the critical section at the same time, which is not what we want to do, right? Questions or confusion? Like you don't understand how the mutual exclusion is not achieved. So basically, the only thing here happening is that these first two statements in both processes, they are executed out of order. So first turn is set equal to j, or in this case 0, and then flag is set equal to true, and same for the process 1. And as a result, if you follow this sequence, follow the sequence diagram, you will see it. You can do it for your own on the notebook. You will see that both the processes enter the critical section at the same time. Okay. So the basic reason is that the instructions are executed not in the specified order, not in the program order, how they are specified in the program, not in the program order, but in the order different than the program, right? So what is the solution? What is the solution? If we know the problem, reason of the problem, if we get rid of that reason, then we can avoid the problem, right? So the reason is that our instructions, they are not executed in the same order as specified by the programmer. Programmer wants first flag 0 to be set equal to true and then turn set equal to j. but our compiler is reordering them. Now, if we have a mechanism to say that, no, don't reorder them, then we can avoid the problem, right? And there is a mechanism which is known as memory barrier. So I will first explain and then I can read the slide. From your face expressions, I can see that the previous example of reordering where we had thread 1 and thread 2 setting x equal to 100 was more clear to you than the Peterson. So I'm using that example to explain what is memory barrier. So remember in thread one, what the thread 1 was doing, it was continuously checking the flag. So if flag is not true, keep checking it. Thread 2, it was supposed to set x equal to 100 and then set flag equal to true. But what compiler was doing, it was saying flag equal to true and then set x equal to 100. And then due to also on top of that, due to scheduling, after the flag is set equal to 2, the thread 2 was kicked out, right? So the value of x was not updated. So the value of x was still 100, still 0. So it sees the flag is true and it prints x. Okay. So how can we avoid? So the basic culprit is reason is coming from here that we are doing the reordering, right? So if I say here, like if I say don't reorder, which basically means do x is equal to 100 and here I'm putting a barrier. So which basically means I'm telling compiler, don't move any instruction which is after this barrier before the barrier. I mean, all the instructions before the barrier, they must be executed before any instruction after the barrier can be executed, right? Which means now this instruction cannot cross the barrier. So if it cannot cross the barrier, this instruction will always be executed first, right? So if now it is executed first, so x will be set equal to 100, and then flag will be equal to true. So when it sees the flag is equal to true, it will print 100, not 0, right? Right? So we here are just like try to present like graphically what the barrier is, but we can specify it through an instruction. So what we do is that here we put an instruction which is known as memory barrier instruction. Simple as that. It is a assembly level instruction, but when you are writing your code at the higher level language, definitely there are like higher level language statements which you can use, which ultimately translate into that assembly level. But it is supported at the level of the hardware. Okay, so the architecture supports this instruction.
Does using memory barriers reduce how parallelizable the code is?
Sorry, say it again.
Does it reduce? We have the equation with like 1 over s plus n.
Dassler?
Yeah.
Yeah.
Does that reduce this because we are not allowed to run the specific part with parallel?
Yeah. So if you look from the perspective of the Amdahl's law, then definitely this barrier is like serializing. It is the serialization point. Let's say you have some code here and some code there. The code here, maybe you can like, if it is independent, there are no dependencies, maybe you can run them in parallel. But then all of that code must complete before this barrier. And then all the code after that only can be run once all this code has been completed. So definitely it affects your parallelization, which means it reduces the performance, which means it takes more time. Okay. And this is the reason, one of the reasons that why that's why the barriers are not preferred, because they put the serialization point in your execution. Okay. So let me now read the slide. Okay, so here they are first trying to build the context and explain why memory barriers are needed. I have explained, but in a different way. Let me just read and then also like explain what it means. So memory model are the memory guarantees the computer architecture makes to the application program. So what does it mean? So basically what we are saying, what memory model is, memory model means that if we have two threads, just like in this example, if we have two threads and they both of them are accessing the same data, global variable, remember that that's why the computer architecture is important. That when you are running the code, you are not running it in space. It is always running on the underlying hardware. So hardware affects it. So keep in mind, like when you are running the threads, there you are running on different core, and they may have their own local private L1s, right? L1 caches. So if they have private L1 cache and thread 2 is updating the X in its private L1 cache, how does the T1 know, thread 1 knows that X is updated or not, right? So if we want to achieve the correct execution, so once the thread 2 updates X1 in its own L1, its X equal to 100 in its own L1, but it has, thread 1 has an older copy of X in its L1, then it will still not print 100, it will print 0, right? So which means that once the X is updated by L1, the other threads running on other cores, they need to be informed that the data is updated, and if they don't have the most latest or the recent copy of the data, they need to bring it from somewhere, or they need to request it, right? So the memory model, actually, it tells us that when the data is updated by one thread on a core, then the other threads running on other cores, at what time they are informed about the update. Are they informed immediately? If yes, this is known as strongly ordered memory model. I have 10 more minutes. This is known as strongly ordered memory model, where a memory modification of one processor is immediately visible to all the other processors. So if thread 1 updates the X in its own L1 cache, all other threads running on other cores, they are informed that the data which you are sharing with other threads running on a different core is updated. Weakly ordered, it is a model where modification of one processor may not be immediately visible to all other processors, right? Definitely, if you immediately, like if I update the data and I'm sharing that data with all of you, and before I can do anything else, I must first inform all of you. I mean, I have to wait for that communication step, right? So I am doing some extra work to inform you, and it will slow down my execution of the program, right? So everything has pros and cons. So as a, like, how to say, compromise, what you can do is that maybe possibly I can relax the requirement that instead of immediately informing you, maybe I can put some epochs or time periods that, let's say, after every 10 cycles, I update everyone else that, okay, this data is updated. All the data which was updated in last 10 times units. So as a result, what will happen that I will not need to communicate with you on every update. I am still updating, but not on every. Still communicating, but not on every update. So a memory barrier is an instruction that forces that any change in memory is propagated and made visible, which means made visible to all other processors. So here, when we are putting the barrier here, and now we say X is equal to 100, thread 2 says X is equal to 100, and then it says, oh, there is memory barrier. Then this X is equal to 100 need to be updated also in the L1 of thread 1. And then when it says, okay, now flag is equal to true, now when thread 1 executes flag, and after that it reads X1 from its L1 cache, it sees the updated value. Any questions? No? Okay, let me also read this one because I think I have explained already. When a memory barrier instruction is performed, the system ensures that all the loads and stores are completed before any subsequent load or stores operations are performed. So subsequent means those which are after the barrier. So all the load and stores before the barrier, all of them must execute and complete before those which are after the barrier. Basically, which means there is no reordering across the barrier. Therefore, even if instructions were reordered, that memory barrier ensures that the store operations are completed in memory and visible to other processes before future load or store operations are performed. Okay, so I think the second statement is a bit confusing, but basically what we are saying here is that compiler cannot, even if your reordering optimization is enabled in the compiler, but you are putting this memory barrier in your code, the optimization will not be applied across the barrier. Only on one side of the barrier you can apply still, but not across the barrier. Okay. This is the same thing which I have explained on the board. So I'm skipping this one. It's exactly same example. Okay. So how can now you use this memory barrier thing to solve that Peterson algorithms problem? Let me go back to the Peterson code. Yeah. How can now I use the memory barrier to solve the problem? What was the problem with the Peterson? That we cannot use it on the modern system because modern systems reorder the statements or instructions, and as a result, two processes can enter the critical situation, critical section at the same time. Yeah, and on like in the code, if you just put a memory barrier between the flag statement where you're setting the flag true and where you're setting the turns variable, if you put a memory barrier, it means you are saying don't reorder them. You are not allowed to reorder them, and since they are not allowed to reorder, as a result, two processes will not enter the critical section at the same time. But on the downside, you are doing something extra. You are doing an extra statement, memory barrier, right? It is itself a statement. So you will incur more execution time. But then always correctness is more important than the performance. Whenever you are like solving any problem, you first need to make sure that you are solving it correctly. And once you are sure, then you can optimize that solution. So like you have a base solution, which is correct, and then you optimize it to get the performance improvement. Okay. So what we can do is now we are actually still talking about the critical section problem. We said, okay, how we can solve the critical section problem. First, what are the three requirements for solving the critical section problem? Mutual exclusion, no deadlock, no starvation, right? And then we said, okay, we can use the Peterson algorithm, which is a software-based solution. Why we say software-based solution? Because we don't need any extra hardware support. But then we saw that it cannot work in the modern systems because of the instruction reordering or out of order execution. And then we said, okay, we can avoid that problem by putting the barriers. However, it means that when you as a programmer, you are writing the code, you need to put these low level statements. So memory barriers are not like, there can be possibly APIs for that, but you need to put those assembly languages instructions in your program, which is not easy, which is not programmer friendly, right? I'm not saying not easy in the sense that you cannot do it, you can do it, but for example, let's say every time you need to make sure that this set of loads and stores should not be reordered, you need to put a memory barrier there every time. So, and if you skip one of them by mistake, your program will not be correct. Okay, so which means that it is error prone. Okay, so what you can do is that you can achieve the mutual exclusion by using locks. So the idea of the locks is that it is very simple, which is already like, I think you are aware of this. What you can do is that you can just, before entering the critical section, you acquire the lock, you do the whatever you are supposed to do in the critical section, and after that you can release the lock, right? Where lock is a entity which is shared among multiple processes or among multiple threads. For all this discussion, we will be using process and threads interchangeably, like they mean the same thing, right? So here is an example. Let's say that we want to implement the lock using a global integer variable, which we are naming as lock and which is initially set equal to 0. And then we have this code for two threads, which are trying to enter the mutual exclusion based on the same lock. So while lock is equal to 1, then keep waiting. But if it is not, then the loop will break and you will set lock equal to 1. Enter the critical section, set the lock equal to 0 after leaving the critical section. Same thread 2 is doing the same thing. But this solution will not work. Why? Not work mean it will not guarantee that the two threads enter the critical section, not enter the critical section at the same time. Why? Why this solution will not work?
All log your reorder and place somewhere else. That's something.
Can they do what?
Like the function call that calls lock to like fetch it. But when stuff gets reordered, can that thing be moved like the whole lines above the to where we don't call it where we want it to be called?
Yes, that can be a reason, but that is not the only reason. That can be a reason, yes. So think about assembly, how you implement this while lock statement in assembly. When you will translate into assembly, it will not be a single assembly hardware level instruction. It will be multiple hardware level instructions. So how will you, let's say, how will you do this lock? Let's say I will move into register 1, the data from memory location at the address of lock, and then branch not 0, test R1. If it is not equal to 0, then which means it is already set, right? So move back to the test. And let's say test is the label of this assembly instruction. You have done the assembly programming. Okay, I think I need to stop. We can continue.